So in the last class, we discussed about embedded firmware. What is meant by embedded firmware? So now, in today's class, we are going to discuss about what are the different embedded firmware approaches which are there. So if you talk about the embedded firmware design, so that particular embedded firmware design approaches is purely dependent on the complexity of the function we perform. So what type of operation you have to perform, what should be the speed of your embedded system, and what are the requirement of the embedded system. So depending upon those design approaches, your embedded firmware design is basically classified into two different approaches. Okay. So two different basic approaches are basically used for embedded firmware design. What are they? One is your conventional procedure based differential approach. So one will be conventional procedural based different firmware design. Other is your embedded operating system based design. So now when you start talking about your conventional procedure based firmware design, so that particular type of design is also called as super loop model. So conventional procedural based firmware model is also called as super loop model. Okay, so let us discuss one by one. What do you mean by super loop model and what do you mean by embedded operating system based design? Okay, so let us come to a super loop based model. So in this particular type of model, the super loop based firmware design development model. So now this particular type of model is designed where there is not time critical is there. So we don't have any time restrictions are there in that particular type of embedded systems. We are going to make use of this particular approach. So and your response time is not that much important. So when it is respect to the time critical comes into the picture, the response time will not be that much critical, which you are going to have. Okay. So now, if you talk about the super loop approach, so if a super loop approach is very similar to your normal procedural oriented languages, which you have been came across. So like your C programming. So if we talk about the conventional procedural programming, so in the procedural conventional programming, what will happen? So there the code is going to be executed one step by one step, or it will be executed one task by the other task. So now, what are the tasks it has to be executed? That particular task will be listed at the top of the program code. So the task which has to be run, so it will be in a list. So the list which the task which is at the top of the program, that will be executed first. So for example, if I take the function, so inside your main function, you're going to have a number of functions, right? So if you're taking, for example, I'm going to have that in C program, I'm going to have functions. In the main functions, I'm going to have function 1, function 2, function 3, like that. Okay, function 1 will be there, function 2 will be there, function 3 will be there. So now it will be executed step by step. Okay, one after the other. So that will be executed step by step. So whatever the program it is listed, that is whatever the task is assigned at the first, it will be executed first. That is the function will be executed first. And after completion of this particular function only, it will execute the function 2. After the execution of function 2, it is going to execute the function 3. So this is what is called as procedural oriented approach, which you are going to have. So now, when you are talking about your multiple task based approach, so when you are talking about the multiple
Excuse me, sir. Your voice is muted, sir.
So now, in this particular approach. Okay, so in the firmware execution, so how it is going to flow is, so here, if you take the firmware execution flow for this, it will be, first it is going to configure the parameters. So it is going to configure the common parameters which are there. So after configuring common parameters, like initialization will be done in the beginning, and it will go to perform the general hardware check. Okay, so that is called as a performance or self test. That is called as post that we are going to have. So performance of self test it is going to perform, and what are the hardwares it is going to be having that particular embedded system. It is going to initialize all those hardware. Okay, all those hardware will be initialized there. All the hardwares will be initialized, and what are the memory is there and what are the registers are there. It is basically it is going to initialize it. So after initializing all these parameters, okay, so it will start executing the task. So first it will start with the first task and it will execute it. Okay, so like what I told in the previous example, like it is going to have the function one. So for example, I'm telling, so this will be executed. That particular task will be executed, and after completion of that particular task, okay, after the completion of that particular task, it is going to execute the second task. After the completion of the second task, it is going to execute the third task. So subsequent task will be executed one after the other. So till it reaches the last task. Till it reaches the last task, it is going to be executed one after the other. So if there, and what will happen again in your embedded system, again it will go back to the first task to execute, because all these tasks has to run infinite amount of times as and when your embedded system is on. Okay, so these tasks has to be running infinitely. So all these tasks will be running infinitely. So that you have to keep it in mind. So whenever we are discussing with respect to the embedded system, all the tasks has to be running in infinite amount of time. So that the game is the same procedure has to be repeated one after the other. Okay. So because that has to be taken decision depending upon the events which is occurring at the outside world. So for that particular reason, one task after the other, it is going to execute. After when it goes to the end of that particular task, again it will go back to the first task. So that same function will be repeating again and again. Okay. So when you talk about the firmware sequence execution, so from the firmware execution sequence, if we take, okay, so it is obvious that the order in which the tasks are executed are fixed, as we have seen here that. So in our procedural oriented language, procedure oriented approach, so whatever the task you have to execute, that particular task which is that particular sequence of tasks to be executed are fixed, and it will be hard coded in the code itself. So that means they are coded inside the code that this particular procedure only have to go. So this particular task itself has to start first and it has to go in that particular manner only. Okay, so in that way it has to execute. So that is how the execution of the task is going to take place. Okay, so next when you are going to visualize, so if you take the code, so you can visualize the operation sequence listed above. So whatever how we have been understood in the previous way, that it has been listed above in the C programming code. Okay, so that if you write in your C programming code, how that particular program will be written. Okay, so from this particular C code, if you are going to have, so always the C code will be starting with void main. So normally the standard procedure which you are going to have is your int main will be there. So if but here there is no return type will be there. Since there no return type is there, we are going to make use of the void main. So void is nothing but what? The function will not return anything to the main program. So now from this particular part of the code, so we can see that the task 1 to task n. Okay, so the task 1 to task n, which is that will be executing one after the other. Okay, that will be executing one after the other. So when the last task is executed, what it will do? So I am writing this particular task inside what? Inside while 1. While 1 is nothing but while 1 is refers to true. So any number other than 0 is referred as true. Okay, inside your while loop. So if it is true, it has to execute the part of the code which is inside the while block. Now, first it is going to execute task 1. Next, it is going to execute task 2. Similarly, it will stop on executing task n. So after executing task n, again the control flow where it will come, again the control flow will come to the while. Again it will check that whether the condition is true or false. Again it is true. Again it will start from task 1. So again it will execute task 1. Again it will execute task 2. The subsequent task will be executed until it encounters the task n. So here the firmware execution is again redirected to task 1 and it is repeated forever in the loop. So in this particular program, you can see it here. So first, initially what it is going to do, initially it is going to do the configurations. So that is necessary configure, that is what are the hardware that is present for that particular embedded system. So I have to look after that particular hardware I have to initialize, because when I am doing the program, which are the necessary units which will be included in executing my program. So that basic initialization has to be done. Okay, these drivers will be there. Those things will be taken care by those things. So now, when you are going to have the repeated functions here, so this is achieved by what? So this what you are, as I told you that already. So this is going to be achieved by the infinite loop. So as I told you that your while 1. So while 1, it is going to specify as what? It is going to specify as the infinite loop which you are going to have. So if you are going to have the infinite loop here, okay, so while 1 is going to have the infinite loop, so then it is going to execute one after the other and it is going to be completing. So that means this loop will not terminate, okay, till you switch off your embedded system. So this loop will be continuously executing at the back end. So till your embedded system is what we can tell. So if it is harmed or if it is goes down or you are terminating that particular embedded system. So till that particular time, the embedded system will be keep on running. So this particular type of approach is called as the Superloop based approach. Okay. So this is about Superloop based approach. So here in this particular task, so since the tasks are running inside an infinite loop. So now, as I told you that the only way to come out of the loop is either by the hardware reset or interrupt assertion. As I told you that either you switch off that particular thing or any interrupt is coming. So hardware, if you want to reset your hardware, so that means you are going to take out the hardware from that particular application and I am going to reset that particular hardware with a new application, or some interrupt is coming. It will stop that particular part of the code. So normally, most of the time, your embedded system, which is working in the Superloop based approach, so they will not terminate. Okay, they will not terminate that one. So so what do you mean by hardware reset? So your hardware reset is nothing but what? It will bring back the program execution back to the main loop. As I was saying, as we have seen in the previous code, so it will come back to the main program. Okay, so when you reset it, it will come out of the while loop. Again, it will start from the main program. Okay, it will start from the main program and it will initialize it. Configuration will be done first. Next, initialization will be done. Next, it is going to enter into the infinite loop. Inside the infinite loop, it is going to execute the necessary task, one after the other. Or the second one, where your program is going to be resetted is, so it is going to, when the interrupt request comes. So if your interrupt is coming means what? Whenever the external interrupt is coming, so whatever the task that presently it is running, so that particular task will be temporarily suspended. Okay, so it is going to suspend the task execution temporarily. Then after suspending the task present which is running, what it is going to do, it is going to serve the routine which is coming. Okay, so whatever the interrupt routine is coming, so that particular interrupt routine it is going to serve. Once that particular interrupt service routine is being served, again it is going to restart this task execution from the point where it has been interrupted or where it has been stopped. So at some part of the task, that particular interrupt will come. So I'm going to stop that particular part and I am going to serve that particular interrupt. So as I told you in the previous classes, it is nothing but what? So you have a system in your HOD's chamber. So some person will be doing, assume that your student is doing some work in the system which is there in the HOD's chamber. Now, some teacher comes to you, so and she or she will ask that I want this particular system. Now your teacher is the interrupt there. So when the interrupt coming, so this is high priority interrupt now. So whatever the work you are doing in that particular system, what you are going to do, you are going to save at that particular part. You are going to save till what you have been done, and you are going to leave the system to the teacher. So now the teacher, what you will do? Teacher will sit on that particular system. She will do that particular task which has been assigned to that particular assigned to her. After completion of the task, she will release the system for you. Once it is released, when you acquire the system again, you are going to start the job from where you have been stopped. You have saved all the things, right? So if from there you are going to start once again the task which is going to be completed. So that is how the same thing which is happening in your hardware system also when the interrupt service routine comes. Okay, so that is what your Superloop design, loop based design is going to work. So normally, if we talk about the Superloop based design, so this particular Superloop based design does not require any embedded operating system. So this particular type of design does not require the operating system. It does not require any operating system. So since you are not having any operating system involved in that one, scheduling will not come into the picture there. Okay, so since the scheduling is not coming into the picture, you should have which task has to be executed first and which task has to be assigned the priority for each task is not there. Okay, so there is need not for scheduling which task is to be executed and assigned priority for that particular task. Since why it is like that? Since in the Superloop based design, all the tasks will be executing one after the other. So you are not scheduling. This particular task has to do first, and this task one has to be done at this particular time. Starts to has to done at this particular time. No, we are not telling. We are not telling that one. So we are telling that one after the other, that particular task has to be completed. And we are not giving any priority here for a particular task since it is going one after the other. So in a Superloop design, so the priorities are fixed. So priorities are fixed means what? The task has to run one after the other. So the task has to run one after the other. So task has to run one after the other. One after the other, that's what it's run. So there will be no priority in that one. Okay, there are no priority in that one. This is the task to be executed are also fixed. Since the task which has to be executed that are also fixed here. So now, since for this one, so the code for performing this task will be residing inside the code memory without an operating system image. So whenever you want this particular type of code to be inserted into your embedded system into the ROM, so whatever the code task we are going to have, so that which we are going to have here. Okay, so this task will be residing inside the code memory without an operating system image. Okay, you don't have the operating system image. Without the operating system image, that particular code will be residing. Okay, so that is how it is going to be working. So next, when it goes to the Superloop based design, so this particular design is this particular design is deployed in low-cost embedded products. So this particular type of embedded products, so where the response time is not that much critical, so it is going to be used in low-cost embedded products. So wherever you are going to have the low-cost embedded product, so you are going to make use of Superloop-based design. So it is where, for example, where you are going to have the electronic video game toy. So where it is contain only keypad and display unit in that particular type of embedded product, you are going to make use of that one. And you are going to have the card reader where you have to read the data and write the data from the card. So there you are going to have to see, check for the sequence of operation, like checking the presence of card, authenticating the operation, and reading and writing. So for example, in this particular type of application, you are going to make use of the Superloop based design. Okay, so your Superloop design is simple and straightforward. Okay, so it is going to have the simple and straightforward approach. So it doesn't contain any OS related overheads. So we are going to, if you are going with OS related overheads, so there are some of the overheads we have to process communication has to be done when the OS comes, scheduling has to come, we have to assign the priorities for that particular task has to come. So these overheads are not there when you are making use of the Superloop based design, since your Superloop based design is simple and straightforward. Okay, so the major drawback of this particular approach is what? So if any failure is there in any of the tasks, because all the tasks will be running one after the other. Okay, so when it is running one after the other, so if any one of the task fails means what? All the other task is going to affect, all the other task is going to be affected, because if that particular task is not completed, so your next task will not start. So if the next task will not start means what? So it will stop there itself. So if any failure of any part of the task is affected, it is going to affect the entire total system. So that is nothing but what? If a program hangs up while executing a task, so that will remain at that particular part only until you are going to reset that particular hardware. So until the product stops functioning, it will be remaining there itself. So the lack of, another major disadvantage of your Superloop design approach is your lack of real timeliness. So that means I don't have the time deadline. So time deadline is not there. So that is one of the drawback. So since that particular whatever task you are going to run, so that has to be run one after the other till the completion. Okay. So there are other several corrective measures has to be done, taken care. So if you want to overcome that particular real timeliness, so what is the other corrective measures we have to give? So we have to use you have to make use of the external events. Okay, so external events you have to do or use interrupts for external events, so which is requiring the real time attention. So some external event is going to come, we have to make use of the interrupts for external events. So when the interrupt comes from the external events, so it has to be taken care at the utmost. So why that means? So when the task is running, it has to say that whether I have to serve that particular interrupt or not. So there you require the real time attention where you are going to have that one. Okay, so that you have to utmostly take care of that one. So that is about your Superloop based approach. So next, when it comes to the next phase of approach is called as your embedded operating system based approach. Okay, so anybody having any doubt with respect to the Superloop based approach? Anybody having any doubt? Anybody having any doubt? Anybody having any doubt in your Superloop based approach? All of you hearing?
No doubt, sir.
Okay, so the next type is your embedded operating system based approach. Okay, so next is embedded operating system based approach. So as the name indicates, this particular approach requires operating system. Okay, so the operating system which you are going to have here, it may be either a general purpose operating system or it may be a real-time operating system. Okay, so it may contain both, either it may be a GPOS, it may use so general purpose operating system or real-time operating system to host the written application firmware. So if you want to host the firmware, so to host that particular firmware, you require either general purpose operating system or you require the real-time operating system. So now if you take the general purpose operating system design, so all of you are studying your general purpose operating system design. So this particular general purpose operating system design is very similar to the normal operating system which you are using in day-to-day life. So that is very similar to the conventional PC based application development. Okay, so which you are using it day-to-day life. So where the device contains an operating system and the operating system which you are going to have, it may be a Linux or Unix or now it is Mac is there. So even that one you can use, or if it is very different flavors of Linux are there, so it will be used for desktop PCs. So and you are going to create your applications, and those applications will be running on top of that particular operating system. So you are going to build one application, and that particular application will be running on top of the operating system. So now, when we talk about the example of the general purpose operating system, which will be used in embedded product development, is Microsoft XP Embedded 8.1. So that most of you have seen in your mobile devices, this particular operating system. So Windows has WinC is there, Windows XP Embedded 8.1 operating system is there. So most of the time, this particular operating system is used in your mobile devices, or it may be used in PDAs, and where PDA stands for Personal Digital Assistant, or it may be used in your handheld devices or portable devices or point of scale terminals you are going to have, and you are going to make use of the patient monitoring system also, it will be used. So these are the places where it is going to be used. So next, when it comes to the embedded operating system, so here, so whenever you are going to have the embedded operating system, so what you are going to, this particular based application, so this particular based application also require driver software for different hardware present on the board to communicate with them. So whenever you are having the embedded system to build, so that particular system, if it is involving the embedded OS, so for all the hardware which are going to connect to that particular embedded system should have a driver. So that is called as device driver. So you may have heard about the device driver. So all the devices which are going to connect inside that particular embedded system, or if you talk about your normal PC also, so you require the device driver to work to make that particular hardware to work, right? So that you have been coming across, I think. So if you are using your USB, it will tell you when you insert the USB for the first time, it will tell that so your device driver software has been installed. So what is that particular device driver? So it is nothing but driver which we will use to sense that particular USB and to display the contents of the USB. So that has to be done.
Excuse me, sir.
So not
Again,
audible.
it's muted, sir.
So now here, so in the embedded system operating system based approach, so I will start from the beginning. So in the embedded operating system based approach, what it contains the operating system. So it contains the operating system, which can be either a general purpose operating system or a real-time operating system. Okay, so it can be a general purpose operating system or a real-time operating system. For what purpose you are going to make use of this particular operating system? To host the application on top of it. So what type of application you are going to have? You are going to have the written application firmware. Okay, so that particular application firmware, what you are going to write, so that particular application firmware will be hosted on your general, either it may be a general purpose operating system or it may be a real-time operating system. So now when it comes to the general purpose operating system design, so here, so it is very similar to the conventional PC based. So it is very similar to the conventional PC based application development. So the where it is the device contains the operating system, and you will create the and you are going to create the image and you are create the application, and the application will be running on top of the operating system. So some of the example of your general purpose operating system which is used in the embedded products are, so your Microsoft Windows XP Embedded 8.1. So normally this particular operating system, embedded operating system, will be used in your portable devices. In your mobile also it may be used. So if some of you have seen like HTC or mobiles, so STC mobile, but you are using your Windows operating system only. So that is Windows XP and the patient monitoring system. So where it will be used in your hospitals, so it will be used. So now when it comes to the operating system based application, so here when it tells about the operating system applications, this particular type of application requires device driver software. Okay, so this requires the device driver software for different hardware present on the board to communicate with them. Okay, you are having the different hardware connected to the embedded system. So if you want to run those hardware, you require the device driver. So your OS-based application requires device driver for different hardware which you are going to connect in the embedded system, and if you want to communicate among them. So now here is the real-time operating system based. So it, as the name indicates, real time. So it demands real-time responses. So that means as and when the event is occurring, the system has to respond. So the system has to respond to the external stimulus which is coming. So then whatever the real-time operating system, it has to be responding. So that should be responding in a timely and predictable manner. That means what? When some event is occurring at the outside, so that particular real-time system has to respond that this is the event which is occurring outside. So then you have to take the response for the event which is occurring at that particular point of time. So it is normally if you take your airbag as the example. So whenever you are going to have the accident, so your real-time operating system, it is going to sense what is the pressure of impact it is there. Depending upon the pressure of impact of the car, so your airbag has to open. So it has to respond. It has to predict that the accident is going to occur and it is going to harm the driver who is going to sit in the front seat. So it has to open the airbag in that one. So what it contains is the real-time operating system. Here, the real-time operating system contains the real-time kernel. So as we already know, that kernel is the heart of the operating system. So your real-time operating system contains the real-time kernel. So it has to respond as and when the event is occurring at the outside. So this particular real-time kernel which is there, it will be responsible for performing what? So preemptive multitasking. So it will be responsible for preemptive multitasking, schedulers for scheduling the task, and to create the threads. Okay, so these operations, this particular real-time kernel has to perform. So now, if we talk about the real-time operating system, so what it has to provide. So if we talk about the real-time operating system, it should also allows flexible scheduling of system resources. That means what? You are going to have the different resources. That means different hardware will be there, different processor will be there, right? So it has to schedule that particular system resources effectively. And when it has to schedule the resource effectively, what is required? So if you want to schedule the resources effectively, so it has to communicate between the tasks. So if you want to communicate, when the resources has to be effectively shared with respect to CPU and memory, and it has to offer some way of communicating between the tasks. So some of the real-time operating system which you are going to have is Windows Embedded Compact. These are the examples. PSOS is there, VxOS is there, TEDx is there, Micro OS2 is there, Embedded Linux is there, Symbian is there. So Symbian is the real-time operating system which was using in your most of your mobile devices. So this particular RTOS is used in most of the mobile devices. Okay, so if you take about if you have heard that one, so almost all your old Nokia mobile were using your Symbian OS only. Okay, that particular is a real-time operating system which was using. So now I am telling that. So these are some of the RTOS. So now if you want to work with respect to some of the RTOS, the important one are VxWorks and your embedded Linux, which is most of the time they are using in real-time world, and Windows Embedded Compact. So these three are important. So this is important. So this VxWorks is important, and this is important. So these are the three real-time operating systems which are frequently used. And these are some of the examples of real-time operating systems which is employed in your embedded product development. Okay, so this is how it will be done. So now, so anybody having any doubt with respect to the embedded OS? Anybody having any doubt with respect to embedded OS? Anybody having any doubt?
No, sir.
Are you able to listen? Students,
Sir.
Yes, sir.
any doubt?
No, sir.
No, sir.
Okay. So the next topic is embedded firmware development languages. Okay. So what are the different development languages you should have? So when you talk about the embedded firmware, so that particular firmware, by using what languages that can be built. So you are controlling your hardware. So when you are controlling your hardware, what type of embedded software or embedded firmware of languages they are going to use. So now, when you talk about the embedded firmware, so what it can be? So embedded firmware can be a target processor or controller specific languages. So that particular firmware can be a target processor or controller specific languages, or it may contain the assembly language also, it may contain the low level language also. So or it may also be target processor or controller independent language. So where you are going to have the controller independent language. Specific language comes with assembly language or low level language. That means all the processor will be having its own assembly code, right? So that is specific. The assembly is specific for a particular processor. If you take any processor for that particular processor, the assembly language is specific. Okay, the assembly language which you are going to have is specific here. It is applied. So each and every processor will be having its own instructions. So with the help of the instructions which they are going to have, you are going to write the language that is called as assembly language. So that is language specific, assembly language specific or low level language. Okay. So next is your target processor controller independent language which you are going to have. So in the target processor controller independent language, we are going to make use of high level language. The high level language which you are going to use there is C, C++, and Java. So these are the commonly used high-level language. So if we take the Java directly cannot deal with the hardware. Okay. So for that one, what you are going to do, what they are going to do is, so in the top end, they are going to write the application using the Java. So by using the Java native interface, you are going to have the interface, Java native interface. So it is going to interact with the other code, which is either C or C++. So this particular code in turn is going to be interacting with your hardware. So that is how your Java will be used for your embedded device. Okay. So the third type which you are going to have is combination of assembly and high level language. So we can mix the high level language with the low level language also. So if you take the C program, so inside the C program you can have the assembly code also. Okay. So that's what it's going to have. So if we talk about the assembly language based development, so since you have already gone through the assembly language, you will be knowing all these things. So the assembly language is a human readable notation of machine language, which you are going to have. Whereas machine language is a processor understandable language. Okay. So machine language is what? So it will be in terms of binary. Okay. So either it is 0 or 1. So that is only the processor understands. So that is also called as what? Your processor understandable language. So where the processor deals only with the binary numbers 0 and 1. So binary machine language is nothing but a binary representation of that one. So if we talk about the assembly language and machine language, so we are told that this is a processor controller dependent. Okay, so this is why it is called as processor controller dependent. When you write a assembly language, so that will be specific for that particular processor. So different processor will be having the different instruction set. With that particular instruction set only, you have to write the program. So that means what? It is a dependent on that particular processor assembly language. That processor instruction set. With the help of the instruction set itself, you are going to write the program. So whatever the program you have written for your ARM core is, you can use it for only for ARM processor. I cannot use the same code for your Intel 886 processor. It is like that. So it is dependent for that particular processor only. But it is not the case if you write in the C language. If you write in the C language, I can use the same program by changing some of the port address to for your 886 also. The same program can be used for your ARM processor also. So there it will become processor independent. Your higher level language are processor independent. So now, when you talk about the assembly language in the assembly language programming, so it is nothing but the task of writing processor-specific machine code in mnemonic forms. As I told that, so it is a task of writing the processor-specific machine code in mnemonic forms. So those mnemonics are converted into actual processor instructions and associated data using an assembler. So you are going to have the assembler. Assembler is going to convert from assembly language to binary language, which you are going to have it. Okay. So that's how your assembly language based development is coming to picture. So here you are going to have the general format of the assembly language instruction. So which will be instruction is an opcode followed by the operand. So this already we have been discussed in your lab code. So where opcode stands for what? So OP stands for operation. So this is called as operation code. Okay, OP stands for operation. So operation code followed by the operands you are going to have. So when you talk about the operands may be either a source operand or it may be a destination operand. So now the opcode tells what? The opcode tells to the processor that what operation the processor has to perform. So depending upon the operands. So the operands provides the data and information required to perform the action specified by the opcode. So in this particular example, you can see it here, move a comma #30. So here what happens, the decimal value 30 is moved to the accumulator register A. So that is with respect to the 8051 register. So your 8051, if you take, it will be having a different register set. Apart from your different register set will be there, apart from your ARM register set which you have been read. So different processor or different microcontroller will be having the different types of register. So in this particular instruction, what will happen? Move A is the opcode. So if you take this one, the move A is the opcode and 30 is the operand. Move A is the opcode and 30 is the operand. The same instructions which are written in the machine language, it will be in this particular fashion. So in this particular fashion. So now in this one, it is bifurcated into two. You can see it here. So first one, the first part is going to be represent the opcode move A. The first part going to specify move A, and the 8-bit binary value represents the operand 30. So the 8-bit represents the operand 30. So if you convert the decimal, 30 means what? So if you are going to have the 30, it will be 16 ones are 16. Remaining 14 will be there. That is E. So if you are representing E means what? It will be 0001. E is 1110. So that will be converted to binary here. That's it. So that will be converted to hexadecimal value and it will be represented. So and the mnemonic IMCA. So it's also example for instruction holding operand implicitly in the operand code. Okay. So the machine language for that particular increment A is this one. So that is out of your knowledge to study that particular part. So now whenever you are going to write the assembly language, as you have seen in writing your ARM code, so it will be written one per line. All the instructions will be written one per line. So this is what the structure. So this already you know already. So a machine code program that consists of the sequence of assembly language instructions. So it contains the assembly language instructions where each statement contains what? Opcode plus operands. So in this one you are going to have what your opcode will be there. So again here if you take this particular part, so what are these here again is the label as we have seen. Add is the instruction, that is upload. So opcode, this operation code, operation, what operation it is performed. So it is also destination operand to where the data is to be moved. This will be your source operand. So the comment line which we are going to give is followed by the colon. Okay, so you're going to have this colon that be after that particular part. So your comment is going to be written. So here label you are going to use for branching purpose, as we are already, as you people already know that label, opcode, operands and comments. So these are the 4 fields of your assembly language programming. Okay, so I will stop here now. Okay, so if anybody having any doubt